When we think about protecting our most important infrastructure, bridges, ships, power plants, we usually think of just slapping on thick layers of paint. But what if protection wasn't about being thick, but about being smart? I mean, really smart, down at the molecular level. Well, that's the whole idea behind ESP 700 Nano Armor. It's a coating technology that's completely rewriting the rulebook on how we fight corrosion.
So right off the bat, here's the fundamental difference. On the left, you've got your traditional coatings. Think of them like a thick wall, just a physical barrier that, let's be honest, is eventually going to crack. But on the right, Nano Armor is something else entirely. It's a molecular shield. It doesn't just sit on top of the surface, it chemically fuses with it, creating this incredibly dense, impenetrable layer at the nano level. It's a whole different game.
All right, so here's our game plan for this explainer. We're going to dig into what this molecular armor really is and the chemistry that makes it tick. Then we'll look at how it holds up in some seriously extreme environments. And this is key, we're also going to cover the super precise application protocol and the risks involved. Finally, we'll tie it all together to see why that level of precision is absolutely critical.
Okay, let's start with that big idea, the paradigm shift. You see, the fatal flaw of traditional coatings is something called microcracking. Over time, these tiny little fractures start to form in that thick barrier, and that's all corrosion needs to get a foothold. It's just the built-in weakness when you're only relying on thickness for your protection.
So instead of that brittle wall, I want you to picture something more like microscopic chainmail. This molecular structure is incredibly dense, all cross-linked, but it's also flexible. It actually moves with the surface it's protecting instead of just cracking under pressure.
So how is this molecular chainmail actually forged? I mean, this isn't just a can of paint drying, right? It's a really sophisticated chemical reaction. Let's break down how it actually builds itself.
The whole process unfolds in a few key stages. First, once you've mixed and applied the coating, it starts reacting with the moisture that's just naturally in the air. That's called hydrolysis. Now, this reaction does release some tiny amounts of methanol and ethanol, we'll come back to that later, but the magic is in what's left behind. The remaining molecules start to stitch themselves together, forging this dense cross-linked network that becomes a permanent part of the surface.
And all of that brings us to what is honestly one of the most important numbers in this entire story, 99%.
ESP 700 is 99% solids. Now think about regular paint for a second. It's full of solvents that evaporate while it dries. And as they evaporate, the paint film actually shrinks, creating these microscopic pinholes. And guess what? Those pinholes are basically tiny little doorways for moisture and corrosion. But with 99% solids, there's virtually no shrinkage, no pinholes. The shield is perfect from the moment it cures.
Okay, that all sounds fantastic in a lab, but what does it mean out in the real world? Let's take a look at the actual performance data, where this stuff was put up against some of the harshest conditions you can possibly imagine.
Okay, this is just incredible. The absolute highest industry standard for corrosion resistance, the C Extreme category, requires a material to survive 1,440 hours in a salt spray test. As you can see right here, ESP 700 was tested for 5,000 hours. That's over 200 days straight, and it passed. It doesn't just meet the standard, it absolutely shatters it.
And it's not just about fighting off corrosion. That nano-ceramic structure is also unbelievably stable when things get hot. It can withstand temperatures up to 200 degrees Celsius, which is about 392 degrees Fahrenheit. That's a huge deal for all sorts of industrial applications.
And the resistances just keep on stacking up. It's completely resistant to harsh chemicals like jet fuel, diesel, and even acetone. It has proven resistance to nuclear radiation. And it's even certified as food safe, so you can use it in industrial kitchens. The versatility is just amazing.
And look, this isn't just marketing fluff from the company. These claims are all verified and certified by AMPP US, the Association for Materials Protection and Performance. These guys are the global gold standard. When they give their seal of approval, it means these performance numbers are the real deal.
So the performance is, well, it's revolutionary. There's no other word for it. Which brings us to the other really important half of our story. What does it actually take to get this level of protection? Because it is definitely not as simple as just opening a can and grabbing a paint roller.
This is where the protocol comes in. To get that certified top-tier protection we've been talking about, you absolutely cannot treat this stuff like paint. It's a chemical system and it demands scientific precision.
The protocol has 3 stages, and none of them are negotiable. First, you've got to prep the surface. It has to be perfectly clean with a final deep clean using 70% alcohol. This is to make sure you get that perfect nanometric bond. Second, mixing. After you combine the parts, you have to wait 8 to 10 minutes. This is called the induction period. It lets all the air bubbles escape and the chemical matrix stabilize. And third, the application itself is incredibly specific.
Now, here's maybe the most critical part of the whole process, the wet-on-tacky method. The second layer must be applied between 45 and 90 minutes after the first one, while that first layer is still just a little bit sticky. Think of it like this. The molecules in that first layer need to still be active, so the second layer can chemically lock into them. If you wait too long and that first layer dries completely, they won't integrate. You won't get that chainmail effect. You'll just have 2 separate layers sitting on top of each other, and the whole system will fail.
That level of chemical precision also demands professional-grade handling and safety, and that brings us to the reality of the risks. We have to look at this material for what it is, a high-performance chemical that comes with a very detailed operator's manual.
And that manual is the Materials Safety Data Sheet, or MSDS. This is the document that tells you exactly what you're working with, and it spells out all the safety requirements, plain and simple.
Remember that byproduct we mentioned that gets released during the curing process? Well, the MSDS is crystal clear about this. The system releases toxic methanol. It can be absorbed through your skin, your eyes, or by breathing it in. And the risk is severe. We're talking irreversible damage to the optic nerve, which can actually lead to blindness. This is absolutely not something to mess around with.
Because of this, the required personal protective equipment, the PPE, is extensive. You need a NIOSH-approved respirator if you're spraying it, liquid-tight gloves, chemical safety goggles, and you need to have an eye bath and a safety shower nearby. This just goes to show you that achieving this revolutionary performance means you have to operate at a professional industrial safety standard, no exceptions.
So let's bring it all together for our final point. Performance demands precision. On one hand, we have a product with almost unbelievable performance. On the other, we have a protocol that demands scientific precision and serious safety measures. So, why is it worth all the trouble?
Well, the return on investment really makes the case. Look at this. For the same extreme level of protection, a traditional system needs 3 or 4 layers. Nano Armor only needs 2. This cuts project downtime from, say, 3 to 5 days, all the way down to just 1 day. And because it's so much tougher, the time between maintenance cycles is effectively doubled. So doing it right once dramatically slashes the total cost of ownership over the life of the asset.
And this really leaves us with a final thought to chew on. Technologies like this offer a massive leap forward in protecting our most vital assets. The promise is huge, but it demands an equally huge commitment from us to precision, to following the protocol, and to safety. So the real question becomes, for our most critical infrastructure, how do we best balance this kind of revolutionary performance with the day-to-day operational reality of getting the job done right?